Greetings to students. Myself is Nikhil Kumar. I am faculty of Information Technology from Ajay Kumar Garg Engineering College. Today's our lecture is based on discrete structure and theory of logic subject. The code is BCS 303 and the topic is sets and relations. Actually, sets and relation is very important for a computer science student basically. In this video lecture, we will discuss sets theory and relations programming. The topic is set. What is set? Set is a collection of distinct objects. Objects may be continuous or distinct, but set contains the distinct elements. For example, attendees in this class or any class, the prime number. Prime number are the numbers that contain special features and unique. So, these are the example of set. For example, if we represent the set with the variable a, so the elements that can be exist in the set can be 1, 2, 3, 4. Okay. These are the objects for the set A. What is the object? Elements or members of the set. The particular elements that exist in the set are called objects, or these are the elements. The set that contains the null value, that means that if the number of elements in a particular set is 0, then that set is called empty set or null set. And for the objects or the elements, we represent it by the phi. Set of all even numbers between 1 to 12, it is also a set 2, 4, 6, 8, 10 that exist between the range 1 to 12. This is also a set. We actually, all the elements that consider in a set, we represent that elements within the bracket. This is the symbol for to represent the set elements. Set definitions. Universe or universal U, set of all possible outcomes. For a particular set, there is a universal U. All the possible case or set elements that can be generated from the set, any set, are the universal set. For example, when we rolling a die, then the possible case that on the face side, that on the upper side, number of possible case will be 6, because the possible case are 1, 2, 3, 4, 5, 6. At a time, a particular time, the number that can be on the upper side can be exist between these actual numbers. So this is the rolling a die example, and these are the set. We can consider it in the set. The number of total subset. We can count the number of total subset from the set elements. If the number of if n is the number of elements that exist in a set, then total subset will be 2 to the power n. Here in this case, the number is 6. So, possible case will be 64. 2 to the power 6 equal to 64. 64 will be the subset. If there exist two set A and B and both have the same elements, then it will be the identical. If all the elements from A is also the elements of set B, then A is subset of B. That means we represent it from this A subset B. A is a proper subset of B if A is denoted as A proper subset of B. For example, for the proper subset, if A equal to 1, 2, 3, B equal to 1, 2, 3 and 4. So, we can represent it A proper subset B. For the union of A and B, we represent A plus B. The symbol is plus, or we can use A union B. For the intersection of A and B, we can use this one, or A intersection B. For the complement of A, we represent A complement C or A bar. It is the sign for the complement of A. For the representation of Venn diagram, it is a union A intersection B. It is A union B. It A complement. If elements of set A and set B don't have any common elements, then the intersection will be phi, and we will represent it A intersection B equal to phi. If all the elements from B also exist in set A, then we represent this one. Finite and infinite sets. Sets can be finite or infinite. A set S is said to be finite if S is thus empty, or if S contains exactly m elements where m is the positive integers, otherwise S is infinite. For example, the set A of the letter of the English alphabets from A to Z, that are the from A, B, C, Z. If AB is the set and the elements are A, B, C to the Z, all the elements, all the English alphabetic characters that are used, so these are the finite in set. Number of elements are limited and fixed, so it is the finite set. If the range is, but if we cannot count the number of elements that exist in the set, then it is called infinite sets, such that all the numbers that are even start from 2. So the range is not fixed. So it is infinite set. Or for, look at this example, I equal to 0 and 1, it is the range 0 and 1, and when we specify x for the x, that is 0 less than equal to x less than equal to 1, that means x की जो रेंज है वो 0 to 1 वेरी कर रही है. So both E and I are infinite. Counting principle. A set S is countable if S is finite, or if the elements of S can be arranged as a sequence, otherwise set S is said to be uncountable. Classes of sets. given a set S, we might wish to talk about some of its subsets. The subset is for a set A, if set A has number of elements, there are 5 elements, and B has a set 1, 2, 3. All the elements that belong from set B is also belong from A. So we can say that B is the subset of set A. So in this example, there is a set S which contains 4 elements 1, 2, 3, 4. A be the class of subset of S which contain exactly 3 elements of S. From these elements, these 4 elements, we consider a pair, the multiple pairs of set number of for the number of elements 3 that exist in a set A, and this is that A is called the class of the set is set of the classes, where class one of the class contain 1, 2, 3 subset for the set S, 1 to 4 for the 1 to 4 is also a subset of S. These are the particular classes that are the subset of set S, and the collection of this one is the set of classes. Power set. For a given set S, we may speak of the class of all the subset of S. This class is called the power set of S and will be denoted by PS. The particular word we will use here P, and P for the power set, and here we use the set. If there is a set whose the name is S, then the power set is represented as PS. The number of elements exist in the power set is the, if number of elements exist in the set N, then the power set, the number of elements in the power set will be 2 to the power N. Suppose S set contains the total numbers n elements, then the power set will be contain 2 to the power n elements. For example, suppose S is a set which contain the elements 1, 2, 3, then the power set for this set will be 2 to the power 3 equal to 8 elements exist, 5, 1, 2, 3, 1, 2, 1, 3, 2, 3 and S. What is S? 1, 2, 3. We can write down 1, 2, 3. So number of elements, that is the, actually these are the classes. Total classes are the 8. It is a power set. What is ordered pair? An ordered pair of elements A and B, where A is designated as the first element and B as the second element, is denoted by A comma B. In particular, AB equal to CD. That means if we take two set A and B such that it contains some ordered pair value, for example, it is A, B, C, and this contains D, E, F. So the ordered pair for this one will be A comma D, A comma E, A comma F are the ordered pair, from where from the first element belongs from the set A and the second elements belong from the set B. Product sets. Consider two arbitrary set A and B, the set of all ordered pairs A and B, where A belongs to A and B belongs to B, is called the product, or it is also called Cartesian product, and it is denoted by A cross B. A cross B, where A and B are two different distinct elements set, and it is represented as A cross B or A Cartesian product B. A comma B, that means that is A belongs to A and B belongs to B. That means the small a represent the elements from the set A and B, here B represent the elements from the set B, exist from set B. One frequently writes A square instead of A square A. A square A. If we use A cross A, that is there are two sets A, and the Cartesian with the using of Cartesian product, we can call it A square. Let A equal to 1 2 and B equal to ABC, then A cross B will be 1A 1B 1C 2A 2B 2C. For the B cross A, here now this will be treated as set A and this will be treated as set B. So for the B cross A, A1 A2 or A1 B1 C1 A2 B2 C2. What is relations? Let A and B be sets. A binary relation or simply A relations from A to B is a subset of A cross B. Suppose R is a relation from A to B, then R is a set of ordered pairs where each first elements comes from A and B, second elements come from set B. That is, for each pair A belongs A and B belongs from B. Exactly one of the following is true. If AB is the ordered pair from the relations R belongs from R, then we say A is related to B. It will be written as A R B. If A belongs from set A and B belongs from set B and there is a relations, then we can be represented A R B. If such type of possibility is not exist, that means that relation is not exist, then we can say A is not related to B. And then the domain of a relation R is the set of all first element of the ordered pair which belong to R, and the range is the set of second elements. Suppose that there is a relation R that exists 1 2 2 4 2 4 3A. So the domain will be 1 3 and the range will be 2 4A. For example, A equal to 1 to 3 and there are two set A and set B. They contain elements 1 to 3 and set B contain x, y, z. Let R is a relation and it is denoted with the values 1y, 1z and 3y. Then R is a relation from A to B since R is a subset of A cross B. With respect to this relation, we can say 1ry. Actually, these are the subset for the function A cross B. Cartesian product for the Cartesian product A cross B contain all the possible results that are shown here with the relations 1x, 1y, 1z, that is considered in A cross B, 2x, 2y, 2z and 3x, 3y, 3z. So R is the subset of the Cartesian product A cross B, and we can use the term 1ry, 1rz, 3ry for this one and this one. But if they do not exist, we use 1 is not relative to x, 2 is not relative to x. Inverse relations. Let R be a relation from a set A to set B. The inverse of R denoted by R inverse is denoted by R inverse is a relation from B to A which consists of those ordered pair which which when reverse belong to R, that is R inverse. For example, for clarification, for example, let A equal to, A is a set which contain elements 1, 2, 3 and B is a set that contains the elements x, y, z. Then the inverse of R will be, this is the relations R. For the inverse of relations R, we can represent y1, z1 and y3. Actually, whatever is represented in the relations, we can invert the value from second to 1 for all the particular ordered pair in the set. Pictures of relations on finite set. We can also use such type of pictures representation for a finite set. There are two sets, set A and set B. So, if there exists a relation from these elements to these elements, we use the term 1. But if there is no any connection or relation, we use the term 0. It is also a representation. We also use such type of pictorial representation. For it is the set A and it is the set B. For 1, there is a relation to y. So we can use such type of representations. For the relation 1y, 1z, 3y. Composition of relation. If there are more than two sets, so we use the word composition of relations for such that if there is a relation A to B and there also a relations B to C exist, so we will mapping A to C in such a way to count a particular relations from more than two sets. So we use composition of relations. We will discuss it in next slides. Let set A contains the elements 1, 2, 3, 4 and set B contains the element A, B, C, D, and there is also a set C that contains the value x, y, z. For a relation, there a relation exists A to B which have the elements 1A, 2D, 3A, 3B and 3D. For the S, there is a relation from set B to C is represented as this. For ROS, we have 1A, there is not A exist. So, for the 2D, there exists DJ, so we use 2Z for a particular ROS relations. It is called the composition of relations. For 3x, we use a 3a. Here, a does not exist, so we use 3b. B exists, so we use 3b, bz, 3z. These are the example of composition of relation. Type of relations. There are some relations in the set theory. Relation are in set A. There exists a set A. Suppose there exists a set A. For this, there are basically three relations: reflexive relation, symmetric relation, and transitive relations. For the reflexive, if AA belongs from, if there exists a element A belongs to A, and there exists a relations R in which A also belongs to R, then it is called reflexive. That means the number of all the elements that exist in the set, any set A, also reflect to itself for the relations, it is called reflexive. For the symmetric, if existence of AB in R implies the existence of BA also possible, will be exist. That means if AB exist in set A, or AB, the elements AB, the ordered value AB exists in a relations R, then there should be BA should be exist in R. That is the particular case, that if a ordered pair exists, its reverse should be also exist in the relation. It is called symmetric conditions. For the transitive case, if existence of BA exists and AC exists, it implies to BC. Suppose that there is a ordered pair AB exists in R and also BC ordered pair also exists in relations R. There should be ordered pair AC exist in the relations R. It is the transitive relations. If these criteria exist, reflexive relation, symmetric conditions and transitive relations exist, then it is called equivalence relations. Binary relation R in set S are called equivalence if it follow these three criteria: reflexive, symmetry and transitive. What is reflexive closure? A closure is said to be reflexive if it contains the property of reflexive nature, it shows the reflexive nature, it contains all the values that belongs to relations R, minimal relation satisfies condition 1 and 2. That means these two should be exist. For example, there is a set A that contains the value 1, 2, 3 and there exists a relation 1, 2, 2, 1, 1, 3, 3, 2. For the reflexive closure, the first condition is that all the elements that exist in the set A, all the elements that exist in the set A should be in the reflexive, that is 1, 1, 2, 2, 3, 3, and all the elements that belong to relation R should be present in the reflexive closure.